welcome back to another video. So in this one, what we're gonna cover we're gonna see how we can solve the Laplace, not the Laplace, the wave equation, the partial differential equation. We're doing it for the MATLAB project, or if you're watching this, it's because it's an example from analysis 2 that we're also solving together as part of the lab exercises. So this is the problem that we have to solve. So we have a laterally insulated bar that's 10 centimeters long. It has a constant cross-sectional area of 1 centimeter square with a density of 10.6 centimeters cubed, grams per centimeter cubed, a thermal conductivity of 1.04 calories per centimeter second Celsius, a specific heat of 0.056 calories per gram Celsius, and an initial temperature denoted by the function f of x. We know that it is kept at 0 Celsius in one of the ends and at 0 Celsius also at the other end with x equals 10. So what they're asking us to find is the temperature as a function of distance and time at later times. I think we're going to do from 0 to 2 seconds once we plot it in MATLAB. So we have to solve this, the PDE. If you already know how to solve this, that's great. We can just go ahead and write the solution, which is seen over here in green. All right, this is our solution to the PDE heat equation based on these initial conditions. So once again, this is the right here, we have the solution to the heat equation in PDE. If you want to see how we can derive this equation, how we arrive to this equation right here, the solution, you can watch my other videos where we did, where we solved this. If you're watching this before I upload it, don't worry, like I will upload it soon. But if you're watching this after I had already uploaded how to solve this heat equation PDE, you should find the link somewhere around here in the description. I will put like a card to it so you can go watch that video. So anyway, so we have these initial conditions where the both ends are at 0. And we have the function given for this problem, f of x is equals to sine of 4 pi over 10 times x. We have some other givens, right, that we already covered. So let's find the solution ux of t for this specific problem. So you can see what we need to find first, it's we need to find where b is, right, for every n. But before that, let's find the constant c square, and then let's see what we get for this one. So this constant c square, if we solve for it, this should be equals to, we have the conductivity. So this conductivity it's 1.04 calories per centimeter second Celsius. And this is divided by the specific heat, which is 0.056 calories per gram Celsius, and multiplied times the density, which is for this problem 10.6 grams per centimeter cube, which after we get everything from here, we should be able to find our solution, which I believe should be around 1.75 centimeter square per second. So that is our value c square. So now let's find our Bn. So you can see that for Bn, we have this equation right here, right? And if we substitute f of x, we get this in y, which is 2 over 10, which is at the length 10, integrate from 0 to 10 sine of 4 pi over 10x times sine over n pi over lx dx. So we have to integrate two signs, a sine times another sign. So you can see that basically if we use that identity that I have, that sine of a times sine of v equals to 1/2 cosines, difference in cosines. We can use that and plug it in, and this is now our new equation for Bn. So you can see we get 2 over 10 from 0 to 10, 1/2 cosine of 4 pi over 10x minus n pi over 10x minus cosine of 4 pi over 10x plus n pi over 10x. So let's see what we get. So we got to do this for every single one of our n values, and then we need to add all of them up, right? Because each one of those goes along with the summation. That's what we have to do. So for n equals 1, we're going to have 2 over 10 the integral from 0 to 10 of 1/2. And this will be cosine of 4 pi over 10x minus pi over 10x. All right. And this is minus cosine of 4 pi over 10x plus pi over 10x dx, which then from here we should get 2 over 10, the integral from 0 to 10 of 1/2, and this will be cosine of 4 pi minus pi, that's 3 pi over 10x minus cosine of 5 pi over 10x dx. So you can see if we factor out the 1/2, we're just gonna get 1 over 10. And if we take the integral of that of cosine, we get sine, right? This will be sine of 3 pi over 10x times 10 over 3 pi minus sine of 5 pi over 10x times 5 pi over 10. Right? That's what we should be getting. And we need to evaluate right from 0 to 10. So after I do that, I'll have 1 over 10. And this will be sine of 3 pi, right? Because if x is 10, so it will be sine of 3 pi minus sine of 5 pi. And this is minus sine of 0 minus sine of 0. All right. So with this, we can see that what will be our value for Bn? Well, sine of 0, it's 0, right? And then sine of any pi is 0. So Bn, not Bn, will be B1. The value for B1 is 0. So let's do then for n equals to 2. So for an n equals to 2, let me just use a slightly different value just here, just to make things different. So we have 2 over 10. Well, if we use the same formula right here, let's factor that one. So I get 1 over 10. The integral from 0 to 10, and it will be cosine of, what is it, 4 pi and pi. So that will be cosine of 2 pi over 10x minus cosine of, once again, 4 plus 2, that will be 6 pi over 10x dx. Once we integrate, we're going to end up again with sine of 2 pi. Oh yeah, and I forgot to multiply in this one. I forgot to multiply times the 10 over 3. If I were over this one, I put it wrong. This one should have been 10 over 5 pi. But either way, you know, they're going to cancel out to 0, so it doesn't make a difference. But don't forget to include them. So, and for this one, we're going to have same thing, right? So sine of 2 pi over 10x minus sine of 6 pi over 10x from 0 to 10. And if you evaluate again, we're going to get that B2 is equals to, once again, 0, because we're going to have sine of 2 pi, sine of 6 pi, sine of 0, so that's still 0. If we do, once again, let me just write here, for n equals 3, we're going to get cosine of pi x over 10 minus cosine of 7 pi, right? 7 pi over 10x. Once again, if you integrate this, you're still going to get sines of pi x, which is, or sine of pi to 0, sine of 7 pi 0, so we're still going to get the same thing. So once again, for this one, we can see b of 3 is equals to 0. So it appears that all of us are going to be equal to 0, but that shouldn't be the case, right? We should get at least one of the values. Otherwise, for this lateral bar, the whole temperature will be 0, and that's not the case. So let's try one more value. Hopefully this works. And for this one, let's gonna try for b over n equals 4. So we're going to get 1 over 10, the integral from 0 to 10, and this will be cosine of 4 pi minus 4 pi over 10. Just going to write everything. So 4 pi over 10x minus 4 pi over 10x minus cosine of 4 pi. We're just going to write it completely. So 4 pi plus 4 pi over 10x. Same thing, right? So from here, we're going to get 1 over 10. And look, we have 4 pi over 10x, or 4 pi minus 4 pi, that's 0. So we have this one, cosine of 0. Right? Cosine of 0 minus cosine of 8 pi over 10x. So we can rewrite this as 1 over 10, 0 to 10. And what is cosine of 0? Well, that's 1 minus cosine of 8 pi over 10x. So we can integrate this, and we should be getting, right, the integral of 1, which is 1 over 10 times x minus sine of 8 pi over 10 times x times 10 over 8 pi, evaluated from 0 to 10. So this is 1 over 10 times 10 minus sine of 8 pi and times 10 over 8 pi. And this is minus 1 over 10. I distributed it, right? And this will be 0 minus sine of 0 times 10 over 8 pi. So this is how it should look like, right? So once again, sine of 0, 0. This is 0, sine of 8 pi, 0. And we're left with 10 over 10, which means that B4 is equals to 1. So if we continue doing all of this for the remaining of if we continue, once again, we're going to get now sine of a negative pi, which is 0, and so on. So I think we might end up getting something like 4 constants down. But, since we were doing the summations, I think for this one should be enough. Adding more terms will just make it a little more precise, but sometimes you can just truncate the series, which is what we're going to be doing here. So now that we know that n is 4 and b4 is equal to 1, we can bring back our series. So let's try what our original formula was. So we have that u of x of t is equals to the summation from n equals 1 to infinity of bn times sine of m pi over l x times e to the negative lambda n squared times t. All right, so let's figure out what the lambda term is. So we know from over here at the beginning, this formula for lambda, which is c times n times pi over l. So using that formula, lambda n, or lambda 4, is equals to, or lambda 4 squared, so we can already substitute everything. It will be equals to c squared, n squared, pi squared over l squared. And c squared, we already know it's 1.75 times n squared, that will be 16. Times pi squared over 100. All right, and let's see what do we get from this. We get 2.76 per second. That should be the units if you do check them out. So then writing my final answer here, I should get that u of x and t is equals to, well, adding the first terms, we're going to get this is equals to sine of 4 pi, that was n, over 10 times x times e to the negative 2.76 t. And this is the equation that you should plug in your calculation. So you're going to put this number in MATLAB, this equation in MATLAB. you can make a matrix for x, a matrix for t, and keep in mind that for x we do need, so x we're gonna do it will be a matrix from 0, right, to 10. We can do it in increments of 0.1 all the way to 10 if you want to. And then we need to another matrix for t from 0 to 2 seconds. You can do any increment, you can do any length. Just make sure that both matrices are the same length. Otherwise, when you do the multiplication of matrices, it's not gonna work out. So whatever increments you use, just make sure you do that. And that way we can do a plot that will give us our solution. So this is what it should look like, what you get on MATLAB. You can see here I calculated my c square. All right, this is, I got my code on top. Your code should be pretty much similar. So you can find c square, you can find u, which we already did, and everything I'm asking you after is just to find a 3D plot in a plot of the heat distribution and time seconds, and then one of the dissipation of the bar, which I think is already given to you. All you have to do is just basically find the plots. Everything within this video has been to calculate the heat equation based from the PDE. Once again, if you're interested in how to solve it, you can go back and watch that video where we solve the actual PDE. But these are what your plots should look like. So we have a 3D plot of the heat dissipation in the bar. You can see if I zoom in, it looks like this. If I was opening this in MATLAB, I could actually flip it and show you all the sides. But I'm going to give you the code as well. I mean, at least those for analysis 2, you can do this code and you should be able to get this information. So you can plug in MATLAB and find it for yourself. And you can see that if we see it from the front, from distance and the x-axis and then temperature and the c, it looks like a sinusoidal wave, right? Which is what our problem should look like. So if you were to plug in one of the values over here in our equation, you will find out that if you put time constant, then our formula becomes just pure sinusoidal. Now you see it from the other side, from time and temperature. If we keep the distance constant, then this becomes just a pure exponential function, which is what we see over here. This is, once again, the temperature distribution, temperature as a function of distance. So at time 0, right at the beginning, this is how the temperature is distributed. As time passes, I think at least for 2 seconds, this temperature basically equalizes and it just becomes 0 once it reaches steady state. And you can see this, right? This is the temperature as a function of time. So I selected that the temperature right at the center at x equals 6, more at the center. And you can see the temperature, we start around 1 degree Celsius. And it decays quickly in about 2 seconds to 0. So once again, this is a really cool application that I like. You guys can do different applications. You guys play with the length, play with the time, play with the functions, and you can see that using this is how we can model, simple objects. And this is just for the one-dimensional function. When we do the Laplace equation in steady state, this is to model a 2-dimensional element, which we're going to see in the other MATLAB project. But at least for now, this is it. I hope that was helpful, and I'll see you guys until the next time.